Thank you very much for the invitation to speak here. By the end of the talk, you'll understand why I started with full circle. I believe in the continuously truncatable talk, so let's start with the talk in a nutshell. There are two kinds of data analysis that people like to do, and in both of them, privacy could be an issue. One of them is things like when we're looking at statistical properties of the data set as a whole. So an example of that would be analysis of census data. And I can't stress too much how important analysis of census data are. Census data are used to allocate hundreds of billions of dollars in federal funds. They're used to apportion representatives to the House of Representatives. They're used for redistricting. They're used in enforcing voting rights legislation. So it's a very compelling scenario. Other examples might be the Consumer Financial Protection Bureau that analyzes loan data for signs of systematic discrimination. Or maybe you're doing AI and you're trying to train a classifier to detect or to distinguish between cancerous brain cells and healthy brain cells. Another kind of data analysis is when you're looking for the needle in the haystack. So an example of that was the Total Information Awareness Program that was supposed to be able to go through troves and troves and troves of data in order to find terrorists. So we're going to focus on the statistical analysis of data. Differential privacy is a tool for privacy-preserving statistical analysis of large data sets. If you want to try to find the needle in the haystack and you want to do this with some sort of privacy, I don't know how to do it, and differential privacy is not the right tool. So our focus is the set on the left. Now, think about what comes to mind when you say a statistic. A statistic is a quantity that is computed from a sample, and it is supposed to tell us about the population as a whole. So we've drawn the sample from the population, and we're going to compute on this sample, and we think that the measurement is telling us about the population as a whole. Okay? So in particular, you would imagine then that if you have two data sets collected independently from each other from the same population, and each one collected with exactly the right methodology, then they ought to be telling you, in some sense, the same thing about the population as a whole. This is sort of why statistics works, right? You grab a set, you study it, you think you understand. You grab another set, you study it, it should tell you the same thing. So statistics feel private, and this is the reason why. The sense of privacy is derived from the fact that any two data sets sampled correctly would tell you the same thing. And therefore, nobody knows I was in the sample. I can claim I opted out. In some strong intuitive sense, this isn't about me. The same thing would have been learned even if someone had chosen an entirely different sample where I wasn't a participant. So statistics feel private. And so you'd think that if all you did was release statistics, everything would be fine. And this is in some intuitive sense on the right track, but it needs help. And we'll see why it needs help, and differential privacy will provide this help. So differential privacy extends this intuition about statistical privacy to all computations, including computations that are carried out on total population counts that are not taken from a sample, but it's really the population as a whole. And that, of course, is the definition of a census. So how do we abstract the problem of privacy-preserving data analysis? First of all, we need some sort of model, and we have a very, very general model. I'll describe it one way, and then I'll explain a little bit why it's so general. I have a data analyst. I don't know my data analyst. I don't know her intentions. Maybe she's wonderful and altruistic, and maybe she's horrible and nasty and trying to compromise privacy. What she is allowed to do is pose queries to the data set. So she poses a query Q1, she gets an answer. Based on what she has seen, she may choose Q2, a follow-up question, if you will, or a follow-up study more broadly. And then she gets some answers, A2. And this goes back and forth. Now, this is such a broad formulation that this admits scenarios in which the analyst is saying, please give me the entire anonymized data set, okay? Or please give me the following sets of tabulations and tables. Or maybe it'll be generate some synthetic data that look like the real data, except, and that have many of the same statistical properties as the real data, but are still privacy preserving. All of those are reasonable, quote unquote, queries. So you see it's just an abstraction. So the idea is we want to allow our analyst to analyze the data set and learn statistical trends about the data while simultaneously protecting the privacy of everybody in the data set and also, in fact, people who aren't in the data set. Now, this kind of statistical analysis of large data sets while preserving privacy is a very old problem. There's a literature dating back at least as early as 1965. So we're going to have a running example. It's going to be flossing. So the question that we want to know is, how many people floss regularly? So let's go back to this just statistics intuition, and we'll say that the question that the data analyst is asking is how many living physics Nobel laureates floss regularly, okay? So your intuition is, well, there are several living Nobel laureates, and so if we get the answer to this, we won't really know which ones actually floss and don't floss unless we get 0 or all of them. So this seems to be privacy preserving, but I'm going to ask a follow-up question, which is, how many male living physics Nobel laureates floss regularly? Now, suppose I have the exact answer to both of these questions. What can I learn? I can learn whether Donna Strickland flosses regularly or not. Okay? So these two big statistical queries, they feel like each one of them independently is very privacy preserving, but when you put them together, you completely compromise privacy. And in fact, there are a number of attacks, and there's something called the fundamental law of information recovery. And the summary of this, it's a body of research initiated by breakthrough work of Dinur and Nissim in 2003. It says that overly accurate estimates of too many statistics is blatantly non-private, meaning where the definition of overly accurate is tied to the definition of too many. If you have lots and lots of queries that you're making, the accuracy can be pretty awful and still you can destroy privacy. If you want to do this attack with fewer queries, you need much more accurate answers. And this also applies to non-interactive systems. So for example, if I were to release a synthetic data set that you should be able to play with and figure out the approximate answers to most statistical questions, you would be able to launch the attack of the fundamental law of information recovery against it. So if you de-anonymize some stuff and let it out, then it's subject to this fundamental law. Okay. Now, that was part one, the definition of differential privacy. This is a picture, who knows who this is? This is a picture of Cecilia Payne-Gaspardin, who was responsible, she was the first person to realize that the stars were made up of much more hydrogen than there is on Earth. And her thesis was initially was rejected because it contradicted established wisdom. But she did get a PhD from Harvard eventually. Okay, so here I have a database. Cecilia Payne is in my database. What do I want to offer to her in terms of privacy? So one thing that you might want to say is, oh, well, somebody interacting with the data set shouldn't be able to learn anything new about Payne that they didn't know beforehand. And this, in fact, is a desideratum articulated by the statistician Tordelinius in 1977 for what privacy should mean for a statistical data set. So Payne might be an extrovert and she might tell stories about herself and publish things on the web and so on, but interacting with this privacy-preserving data set shouldn't tell you anything new about her. So that's a nice definition, and it's reminiscent of the definition of semantic security from cryptography, but there's a problem. What is the point of data analysis if it's not telling you something new about people? So a little bit more precisely, suppose I'm from Mars, and I actually believe that all humans have 2 left feet. I'm wrong. I don't know that. And I analyze this data set in a privacy protective way, let's say, and I learn that the vast majority of humans have 1 left foot and 1 right foot. So whereas before I believed that Payne has 2 left feet, as a result of this, I have learned that she probably has 1 left and 1 right. I have learned something about her that I didn't know before I interacted with the data set. Is her privacy compromised? Well, that depends on your point of view. So we chose the point of view that this was not a privacy compromise, that this was a fact about the population as a whole and not a fact about Payne exactly. So we formalize it by saying, for example, that we would learn the same things if Payne were replaced by, let's say, another random member of the population. This is Cecilia Swan-Leavitt, who understood a relationship between the period of variable stars' brightness and their brightness. And this turned out to be very useful in measuring distances across space. So ideally, we're going to learn the same things if Payne is replaced by Swan-Leavitt. And in general, we should learn the same things even if the database is perturbed slightly, no matter how you perturb it. So from the point of view of Payne, maybe we could say that we have privacy if the following is the case. Imagine that we have an ideal world. This is ideal from Payne's point of view about her own privacy. So in the ideal world, she has opted out of the data set, and there's no information in the data set about her specifically, all right? And what she would really like is that from the point of view of the analyst is unable to tell the difference between the real world, where Payne is included, and the ideal world, where Payne opted out. That feels like privacy to us. So that's essentially what differential privacy says. It says that the outcome of any analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the data set. So this, in fact, holds even against an adversary who knows both data sets in their entirety. That adversary would still never be able to distinguish. So what is the source of this word likely, essentially equally likely? Where's likelihood coming from? It's coming from our algorithms. So our algorithms will flip coins. They will intentionally randomize. And so when we say that 2 events are essentially equally likely, we mean over the probability space induced by the coin flipping. So this is good because the coin flips are under the control of the algorithm. It's not some sampling or maybe something in the data. It's actually under the control of the algorithm. So what's a good analogy for essentially equally likely? How should I think about this? Imagine that you have 2 coins. One of them is perfectly fair. Okay, so really when you flip it, the probability of heads is a half, which I've written as 500 over 1,000. And suppose the second coin, and don't ask me how this happens, but suppose the second coin is constructed so that it is slightly biased towards heads. The probability of heads is now 501 over 1,000. So if I give you one of these coins and you flip it, this flipping is going to produce either heads or tails. And the probability distribution on the outcomes is essentially the same. It's very, very, very close. And if you just have one coin flip or a couple of coin flips or 10 coin flips or 100 coin flips, you're probably not going to do much better than 50-50 at guessing which of the two coins you have. You just don't have enough information yet. So the probability distributions over even sequences of coin flips are essentially the same for short sequences. And that's what's going on in differential privacy. So, right, I just told you this. Okay. So differential privacy separates harms that can come from things that are learned from harms that can come from being a member of a data set. So people can be harmed based on the outcomes of statistical analyses. Let's say once we've learned that smoking causes cancer, smokers are harmed because their insurance premiums are higher. Now, it's true, but it's also true that the smoker is harmed whether or not she was part of the study that led to the conclusion that smoking causes cancer. And the whole point of statistical data analysis is to precisely learn things like smoking causes cancer. That's why we do it, so that we can, say, encourage smokers to join a smoking cessation program. So differential privacy separates the harms that come from the statistical facts that are learned from any harm that could come from being a member of the data set. And it ensures that no harm can come from being a member of the data set. And just for those of you who clearly a lot of you do know something about machine learning and generalizability, differential privacy is a notion of stability, that you learn the same things even if you perturb the data set a little bit. And that's actually necessary for generalization, to generalize beyond your training set. If you learned different things, if you made small changes in your training set, you wouldn't generalize to the population. And so despite the intuition that privacy and accuracy or privacy and utility are at odds, we see that it's not really the case, especially in the machine learning setting. Privacy can actually help you to be sure that you're not overfitting. It will ensure that you're not overfitting. Privacy and generalization are aligned. So here's the definition. A mechanism is just an algorithm. And I have to tell you about a few things here. So first of all, a pair of adjacent data sets are data sets that are almost identical. It's just that one data set has the data of just one more person than the other. So the data set with pain versus the data set without. That's a pair of adjacent data sets. I don't know why that happened. Okay, so a mechanism, our algorithms have a parameter which is usually called epsilon. And the algorithm has epsilon differential privacy if for every pair of adjacent data sets that differ in the data of just one person, and every possible event, S, the probability that we observe S on the data set X, I don't know why it's doing this. It's advancing. Okay. The probability that we observe S when the data set is X is at most e to the epsilon times the probability of that same event when the database is Y. So this is where epsilon comes in that factor e to the epsilon. And notice that this was true for all x and y, so if I switch the roles of x and y, I get the other inequality as well. So their ratio is constrained to be within e to the epsilon and e to the minus epsilon. And the randomness in these probabilities is what's introduced by the coin flips in our algorithm. So e to the epsilon is about 1 plus epsilon when epsilon is small, so you could think of it this way if you prefer. And you can see that when epsilon is very close to 0, these probabilities are almost the same. And in fact, if epsilon were 0, we would have no privacy loss, and the probabilities would be identical, which makes sense. And this is a statement that's about the behavior of the algorithm. This guarantee on these probability ratios is a property of the algorithm. It doesn't care who knows what your adversary or analyst knows, not now, and not even in the future. So it's an incredibly strong guarantee. So differential privacy does permit you to learn about pain. You just can't learn anything about pain that you couldn't have learned without her. So that's the definition. So going back to the needle in the haystack, if you think of a database X as being the haystack containing the needle, and the database Y as being the haystack without the needle, then differential privacy says that you see the same things with essentially the same probabilities in X and in Y. So of course you're not going to see that needle. You won't even know that it's there. We designed the definition very carefully to protect even the wildest outliers, because often it is the outliers precisely who most need the protection. Average case protection is really not what we're interested in here when we're trying to encourage people to feel safe about allowing their data to be used. Okay, so key properties, I already mentioned that it's future-proof, that it's resilient to present or future information from other sources, and later we'll see also computation. It also composes gracefully and automatically, so we can understand how privacy loss accumulates as we ask question after question after question of the same data. So remember, the fundamental law said overly accurate answers to too many, blah, 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 blah. So what differential privacy does is it keeps track of that privacy loss and tells you when you have to stop before you get to a dangerous place. Because we understand how privacy losses add up, we can build a bunch of differentially private sort of subroutines, and we can program with them. Just as when you do ordinary programming, you don't sort of go straight to the end. You break the task up into pieces, and you combine them, and you try to find ways of doing this that minimizes some resource of interest, like time. And here we want to minimize yet one more resource of interest, which is privacy loss. So for a given task, there may be many, many different differentially private algorithms, and we choose according to the cumulative privacy loss that they offer. Okay, this programmability is something that no other definition of privacy gives you access to. So, as I mentioned, there are many techniques for achieving differential privacy. I'm going to tell you about one of them, which is the addition of symmetric noise. So let's look at, since we're interested in the census, what's the population of Washington, D.C.? So here's a table published by the census, and this is a population estimate on July 1st, 2017 of 601,723. So I'm going to take that estimate as the so-called true count. And how would I release this information in a differentially private way? So here's the real line, and the true answer there is marked with a red star. Now, suppose I had one person opt out. That would actually move the count from 601,723 to 601,722. Now, what we're going to do is we're going to add random noise to the count. The true count, remember, is 601,723. We're going to add random noise, but in some sense it's going to be fat enough in its distribution to obscure whether we started with 601,722 or 601,723. And also, by the way, 601,724. So this is the probability distribution on outputs when I add my random noise starting at 601,723, the full count. And this might be my probability distribution if I were to have added noise to the diminished count 601,722. So that's the opt-out business. And the intuition in this picture is supposed to be that the probabilities are fairly close for any particular value. So a little bit more rigorously, how fat should these curves? I gave my curve a bump. How fat should that bump be? Well, one person can affect a count by exactly 1, right? If I opt in or opt out, that will change a count only by 1. We call that the sensitivity of the function. In this case, the function is just the count. So the sensitivity of this function is 1. Now, that's going to be one of the things that we have to keep in mind. And the other thing we have to keep in mind is how tightly do we want to restrict the privacy loss? If I want very, very little privacy loss, then I want to fatten those curves way out so that the probabilities really become almost the same. And if I'm willing to live with more privacy loss, I can have much more of a peak to the curve. So that quantity is controlled by epsilon, and it's basically the algorithm designer's choice or the policy setter's choice. So the answer turns out to be that the standard deviation should scale with the sensitivity divided by the privacy loss. And just to see that this makes sense, if adding or deleting my data would radically change the value of the function, then we need a very fat curve to hide that change. And also, so there's the sensitivity in the numerator, bigger numerator, fatter curve. If I want very, very good privacy, then epsilon gets smaller. And there's epsilon sitting in the denominator. So small epsilon, again, it blows up the standard deviation, makes the curve fat. So everything's sort of in the right place. And the right distribution turns out to be the Laplace distribution described here. And its standard deviation is square root of 2 times the parameter for the curve, which is delta over epsilon. Okay, so I was going to give you more examples, but I have 3 minutes left. So I want to move on to, we can talk about defeating the differencing attack. So let's go back to our flossing attack. How many living physics Nobel laureates floss regularly? And how many male living physics Nobel laureates floss regularly? Well, the sensitivity of this pair of queries is 2. And I haven't gone through how we're defining sensitivity for a vector-valued query, but it's the L1 difference in the norms. So basically, one person could change the answers to each of these questions by 1 for a total of a change of 2. So the sensitivity is 2, and again, we use Laplace noise scale to 2 over epsilon. Okay. Now, full circle. So when we started this work in 2002, the Census Bureau was our driving scenario. It's the data of the people allocated for the benefit of the people with a legal mandate for privacy. So we didn't have to convince them to use privacy. They wanted to use privacy, and they have been using privacy. So fast forward to the upcoming 2020 Decennial Census. This is John Abad, the chief scientist at the Census Bureau. And this is a quote from a talk that he gave just a few weeks ago at AAAS. Basically, what he says is that the techniques that they used for the last decennial census no longer suffice. He says, technical advances revealed a new vulnerability, allowing people to reconstruct data from tables that were previously assumed to be privacy preserving. You know what that is. That's that attack behind the fundamental law. So they woke up and they said, oh my gosh, there's this fundamental law, and they tested it out, and indeed they were able to attack their own 2010 data release. And they could even do more when they used publicly available commercial data from the same time. So this is why the census is using it. And the algorithms that they're going to be using in the 2020 census are beyond the scope of the talk. There are a number of questions that come up. How do you choose the privacy budget? And how do you allocate the privacy budget among competing statistics, statisticians, analysts, and so on? And the very few last seconds, Steve Feinberg, the late Steve Feinberg, really impressed on me that statisticians or people who are used to analyzing data aren't used to working through a privacy-preserving interface. They're used to things like microdata, synthetic data maybe, or enclaves of some sort. And enclaves and synthetic data are very, very challenging, but they're also really exciting ideas recently in this area. So for example, for the microdata generation, people are starting to look at GANs. And with that, I thank you for your attention.